Okay, in this video I'm going to explain some of the answers for the exercise that I set in week 8 to do with infinite sets, which relates to the proof that I gave you for non-computable function. So let's have a look at the answers. So the first one, in part A, you're asked to define what is meant by a finite set. Basically, a finite set is one where if you try to list the elements, you will stop. So basically, it ends. You try and list the elements, they may go on for a very long time, but if you've got enough time at your disposal, you will eventually end. The difference with that and an infinite set, so an infinite set, it will never end, no matter how much time you've got. So the number of grains of sand in the Sahara Desert is a very, very large set, but it is not infinite. An infinite set never ends. Infinite, it means there is no end. No matter how much time you've got. But countable means it has an interesting property. You can align it aligned with the natural numbers. We'll use n0. So you can form a mapping between the elements of your set and n0. We'll see that in a minute. Whereas an infinite uncountable set, well, infinite is as above. It never ends, no matter how much time you've got. But uncountable, it cannot be aligned with n0. There's too much of it. It can't be aligned with n0, and we'll see examples of those sets as we go through the exercises. So those are the three types of sets: finite, infinite and countable, infinite and uncountable. So in the last part of the exercise I gave you 9 sets and I asked you to classify them as either finite, finite there so we can remember what that one's about. It's finite, or the set is infinite and countable, or it's infinite and it's uncountable. So the first one is an easy one. It's the set of all students taking CS 103. That's easy, it's finite. There's 185 of you this year, but there's never going to be an infinite number of students, no matter how many turn up. I'm not going to get an infinite number of students because there's only a finite number of human beings in the world, and there's only a finite number of human beings who's ever lived. So I'm certainly not going to get an infinite number of students taking this class. Now the second one is Theorems of Miu. Now the Theorems of Miu, let's write it here, Theorems of Miu. Well, if you remember about Miu, you've got a doubling rule. So if mx is a theorem, then mxx is a theorem, where x is a variable, a schema variable. That means you can double and double and double and double and double and double, and you can keep going as long as you like, and that proves that there's an infinite number. So it's clearly infinite. The question is it countable or uncountable? I'll move over here, and what we can do, so this is Miu theorems. Let's think of a mapping. Well, the shortest Miu theorem, if you remember, is Mi. That's the axiom. Let's call that number 0. Then you'll remember that Mii, that's also a theorem. Let's call that number 1. Mi MIU is a theorem, that can be number 2, MUI, number 3. And then after that, well, MUU is not a theorem, MU is not a theorem, so that's all the theorems, all the theorems of length 1, sorry, of length 2, because of the M as well, and that's all the theorems of length 3. MUU is not a theorem, so that's not in here, and MU is not a theorem. So the next one would be M3Is, but if you've realised that's not a theorem either. So the next one would be MIIU, and that can be number 4. Then I can have MIUI, let's call that number 5. And then MIUU, that can be number 6, and so on and so on. So clearly I've got a mapping between the theorems, all of the theorems of MIU, and the numbers. I can make a mapping, therefore it is countable. That's what it means to be countable. Basically, I can assign a natural number to each and every member of the set. So this is the set of all theorems. These are the natural numbers. I can make the mapping. I'm good. The next one that I asked you to consider is the prime numbers. Now, I've already proven to you, good old Euclid has proven to you that this is an infinite set, so you know that. The question is it countable? Well, you might think, well, it's actually a subset of the natural numbers, so it's sort of smaller than the natural numbers. But in fact, this doesn't apply because both sets are, in fact, infinite, and therefore, because they go on forever, checking to make sure you can see that, yep, you can indeed. Because they go on forever, here's the prime numbers, 2, 3, 5, 7, not 9, because that's 3 times 3. Then we've got 11, 13, not 15, 17, 19, not 21, 23, not 25, not 27. So the next one after that is 29, 31, and so on. Now you'll know already, due to the Euclid, this sequence goes on forever. Forever and ever and ever. And it really must mean it goes on forever. So I'll just number them. I'll just say, okay, I'll call 2, that's the 0th prime number, and 3 is the index 1. In other words, I'll just index into them. That's the 5th, the 6th, the 7th, the 8th, the 9th, the 10th, and that's 31 is the 11th prime number, so it gets the index 10, so I'm starting at 0, and so on. Here is my mapping. Now, if you give me a prime number, give me a big prime number, say, I don't know, can't think of a big prime number, 97. All I would do is I would go down here. 97 is a prime number, but let's say it is, I think it is anyway. Let's go down here, find 97, and I look up to see which one it is. Similarly, if you say, what's the 101st prime number? I just go down here, look up the 101st prime number here. So in other words, it's a one-to-one mapping all the way along, and that's what means it's countable. Okay, next one is number 4, and I said the set n, so I was just using n, such that n is a member of the natural numbers starting at 0 and n is less than 5. Well, you can see that that's the set 0, 1, 2, 3 and 4, so therefore it's finite. It's really just me testing to make sure you understood the set builder notation. Okay, the set of all the real numbers, reals, that's uncountable, so infinite first. We know that there's an infinite number of real numbers. When we do our x, y axes, the real numbers are all the possible values that x could have and all the possible values that y could have. So x is a real number, y is a real number, anywhere in here, is a pair xy, where x is a real number and y is a real number. We know it's infinite. I also showed you in the video that it's uncountable because you can't form a mapping like this. The diagonalization argument shows you that that's the case. So let's have a look at the next one. Set of all dogs with 4-letter names. Dogs with 4-letter names. Well, here we're assuming that the letters are chosen from a finite alphabet. So that means, let's say there are k characters in the alphabet. Okay, so that means for the first letter there are k choices. Second letter is the same, and so on. So in fact there is k to the 4 different possible names. And k to the power 4, because k is a finite number, k to the 4 is a finite number, so therefore it's finite. Next one is the set of all possible subsets of n. This is very tricky. Set of all subsets of n0. Well, the question is, okay, so here, over here, I've got, that's the set n0. How could I possibly specify a subset of n0? Well, if I imagine n0 here, I'll go 0, 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, and there's lots and lots more, an infinite number. So how would I specify a subset? Well, what I could do is I could say I can specify a subset as a binary list. I could say, okay, if 0 is in the subset, I'll put a 1 here. If 1's in the subset, I'll put a 1 here, otherwise I'll put a 0. So let's say that 1 is out. Let's specify the subset, all the even numbers, for example. So 0 is an even number, so that's a 1. So this is all the even numbers that are members of n0, all the non-negative even numbers. So I'd specify this subset like this. So in other words, it's an infinitely long binary string. That's how I specify a subset. Just as and this is just one subset. Now what you can see probably, I hope, is that if you've got an infinitely long binary string, that's going to behave very similarly to the infinitely long set of decimals, which is the real numbers. It's just that you've got 1 and 0. In other words, the diagonalization argument is going to work again on these subsets. Or you could have just looked it up and found out that the set of subsets of n0 is infinite, and it is indeed uncountable. So it's another example of an uncountable set. So the number of subsets that you can get from n0 is in fact uncountable. What's the next one? 8. So that was in fact the hardest one. The set of all computer programs is easy. Programs are strings. All every program that I've ever written has just been a string of characters. Programs are strings. And we showed when we looked at the dogs and the collars that we can map between strings. In fact, we've done it here again. We can map between strings and numbers. We just list all the strings in order, shortest first, alphabetical. So therefore it's infinite. But it's a countable infinity because we can map between computer programs, which are strings like MIU, and the natural numbers. So it's infinite and countable. And then finally, the functions from n0 that map onto members of n0. So that was the proof that I gave you in the other lecture on the diagonalization argument. And we showed that that's infinite and it's uncountable. You cannot map it to the natural numbers. And what this means is that these two facts taken together, the fact that the computer programs are infinite and countable, but the number of functions that you might like to have from n0 to n0, the fact that that's infinite and uncountable, this means that there are such things as non-computable functions. So non-computable functions exist. That's the ramification of those two sets there.